right, great, thanks. What is OChem? We say it's the chemistry of carbon compounds. Johann Way here was the first person to kind of coin the term organic chemistry. And he says it's the study of compounds from living organisms like sugar, wax, plant oil, and urea, which is a big thing. Anybody know what urea is? It's how your body gets rid of nitrogen when you eat proteins. It comes out in the form of urea. He coined a lot of terms that we use today, like catalyst and polymer, and I guess he suffered from gout. Of course, back then, if you were able to take on study, you typically came from some type of means. Everybody else was like a poor farmer. Now, here's the guy who gets a lot of credit for everything. Wöhler is known for his seminal contributions in organic chemistry. In particular, he took an inorganic substance, this ammonium isothiocyanate, and he heated it up and he formed urea. So he made a compound that was originally thought that only a living organism could make urea, and he formed it in a flask using inorganic starting materials. So we say he undid this vitalism belief that they had at the time. Organic chemistry usually has some other things besides carbon: hydrogen, oxygen, nitrogen, sulfur, phosphorus. Sometimes you can rearrange those to spell the word schnapps. That helps some people remember. So here is a compound that almost looks like the neurotransmitter serotonin, and we see nitrogen. Here is nicotine, and here is just plain old methane, a one carbon chain, methane, an alkane. Now, of course, when I look at these, I see no asymmetric carbon. Right here I see an asymmetric carbon, so that means this molecule has a mirror image, which isn't itself. Just as a left-handed glove isn't a right-handed glove, but they each got 4 fingers and a thumb. Exciting things to come. Here are 21 amino acids, and you can see some interesting things. A lot of nitrogen here. Here's arginine, and this thing is kind of drawn as a resonant hybrid. So I remember taking biology, learning about some of these, but I took biochemistry and we had to learn all these structures. So what are some interesting ones here? How many of you like Chinese food and like to eat lots of MSG? Monosodium glutamate. It's basically a salt of this protein. You get a lot of it in soy sauce. It makes everything taste good. So we said sulfur. And we're going to learn how, cysteine has a sulfur, and this was something new. I didn't know selenium was there. Tyrosine, tryptophan, that thing over there I said almost looked like tryptophan, or serotonin. So I believe your body makes serotonin from tryptophan. And look at that. I believe if the OH was gone, we'd have the neurotransmitter serotonin. What about phosphorus? All right, so where do we find phosphorus? Oh, looky here. Here's a phosphorus. Here's a phosphorus. There's a phosphorus. And you'll recall PO4 3- is phosphate, right? So here's a phosphate sugar backbone and another one. And here are what we call the 4 base pairs. Can anybody name this famous molecule? Right. Here's DNA. All right, as of a year ago, there's estimated 20 million organic compounds known. Chapter 1 has a little bit of a review. What is an orbital? It's where there is a high probability of finding an electron, and we get these space-filling diagrams, and we say, all right, well, we have these atomic orbitals. And so you've all heard of the s orbital, the 1s, it's like first row of the periodic table. And as the principal quantum number increases, so does the size of the orbital. So that second row, we start filling up the 2s, and we come over to the p orbital set. So there's these 3 along the 3 axes. And how many electrons can you put into an orbital? 2 max. Think of those little square boxes, and you'd put the arrows pointing one up and one down. And so 3 orbitals, 2 each, that's 6 electrons, and of course the p block on the periodic table has 6 columns on it. Alright, well, what do orbitals do? They hybridize, and then they're used in bonding. When atoms bond with other atoms, hybrid orbitals are used. So we think mainly about the second row of the periodic table. We call it the second period. But you might have learned for every atomic orbital you mix, you get the same amount of hybrid orbitals. So here we mix an S and a P. So that means we get 2 sp hybridized orbitals. And so here's an artist's picture of what they look like. Of course, they're placed on a central atom, so you don't see this other part. It just looks like you're like a normal atomic p orbital. Now, what you want to be able to do as OChem students is to recognize when you have sp hybridization in a structure. Of course, the easiest way to do that is look at its shape. If it's tetrahedral, it's not sp. If it's flat and planar and 120, it's not sp. If it's linear, in this Lewis structure here of carbon in the middle would have an sp hybridization occurring. And we don't care about those other pi bonds. We can just imagine 2 of those dashed lines, this load being one line, this load being the other, and we won't go over pi bonding right now. Alright, so once again, if I mix 3 atomic orbitals, s and 2 p's, I'm going to get 3 sp2 hybrid orbitals. And of course, they're separate. Each one of these can hold 2 electrons, but they show up around a central atom like this. Looks like a flat plane or triangle. And so here is a Lewis structure. So when I look at that carbon and I see its shape, I immediately know it is sp2 hybridized. Look at its shape and realize that's what's going on there. Finally, if I use up all the p orbitals, p atomic orbitals over there in the p block, I mix an s, 3 p's, that gives me 4 hybrid orbitals, and they all take a tetrahedral shape. And so methane, I look at it and I see 4 groups around there, realize it must be sp3 hybrid. So here's something that might look a little misleading. This is cyclohexane. You might have heard of the hexagon. In OChem, hex means 6. Heard of the hex nut? That's what it looks like. I know those carbons are sp3 hybrid or hybridized. That's the hybridization of the carbon. Alright, so here's a little review. You figure out these electron configurations. Let's just go over bonding real quick. Ionic bonding, we say atoms transfer or share electrons in such a way to obtain a filled shell of electrons. If we went back and looked at the electron configuration, we'd see 1 valence electron for lithium. We'd see 7 for fluorine there. Half barrel. It's just the movement of 1 electron. We'll go over that in a little bit. So here, lithium has a positive charge. Fluorine atom has become fluoride, has that negative charge, and there's that electrostatic attraction, holds those together. Important thing is each element now has a noble gas electron configuration. Alright, covalent bonding. Here is a hydrogen with its 1 valence electron, carbon with its 4, and we can imagine 4 hydrogens coming around there, sharing their electrons. Everywhere we see a pair of electrons, we can make a dashed line to represent a covalent bond. So now carbon has 8 electrons around it, and it has the electron configuration of neon, and so it feels happy and complete. We say it's obeying the octet rule. Alright, so I covered up those electron configurations. We don't need to look at those. But considering the rule of 2 for hydrogen and the octet rule for all the other elements, and we're going to focus on the organic ones, oxygen, nitrogen, and carbon, and halogens, we'll look at that one. We won't worry about helium. And of course you could say helium has its 2 electrons, it's happy, it's a noble gas, it's not going to form any bonds. What do you think? Love, how many bonds do you think carbon will form? Very good.
I know that one.
I picked on you because I didn't think you would be embarrassed, but I figured you'd probably know. So notice here, what do 4 and 2 add up to? 6. And then I get a full octet. And alright, I look here and I say I got 5 valence electrons. To get to 8, I need to borrow 3 more electrons, so nitrogen likes to form 3 bonds. I look at oxygen, I got 6 valence electrons there. I can have 8. So 2 more electrons can come on. So oxygen is We're going to want to form 2 bonds. The halogen fluorine with 7 valence electron can take on 1 extra electron, so it likes to form 1 more bond. So here we see partial Lewis structures for each element that we're going to encounter quite a bit in OChem doing its thing. Carbon forming 4 bonds, nitrogen forming 3, oxygen forming 2, hydrogen forming 1, chlorine forming 1. All right, how many of you like to break all the rules? Good, none of you do. You're all good kids. All right, now that we know that carbon forms 4 bonds, nitrogen forms 3, oxygen forms 2. We're going to break the rules. These are the number of bonds in an uncharged compound. How do we understand charge? Well, we have this formula for formal charge. You should have seen it once before, but it says formal charge equals the group number minus all the non-bonding electrons. Bonding electrons are shared, so I only get half of them, 50-50. So here is oxygen. And you'll say, oh, here's our friend, hydronium ion. How many bonds does oxygen have? It's bonded, it's got 3 hydrogens bonded to it. You just memorize this in Chem 1 and Chem 2 because it was a polyatomic ion that you had to memorize. But here's how we could calculate the formal charge. Oxygen has a group number of 6. All right, I count 2 non-bonding electrons, and then here I see 2, 4, 6. Those are the bonding electrons, but I only get to count half of those. So half of 6 is 3. Negative 3 and negative 2 is negative 5. 6 summed with negative 5 is a positive 1. So there's the charge on hydronium. Let's just throw water in there to check our math, make sure we understand formal charge. Same group number, Roman 6, above that column where oxygen is found on the periodic table. 1, 2, 3, 4 non-bonding electrons. 2, 4 bonding electrons, you get to count half of them. Half of 4 is 2. Negative 2 and negative 4 is negative 6. 6 summed with the negative 6 is 0. All right, here's another thing you just memorized. You probably wrote an OH, superscripted negative, called it the hydroxide ion. Maybe I should have made my Lewis structure go the other way. And it has a negative charge, because we just memorized it. But we could plug it into our equation. Formal charge equals group number 2, 4, 6. 2 there, half of 2 is 1. Negative 1 and negative 6 is negative 7. 6 summed with negative 7 is negative 1. All right, then we have the oxide ion. There it is. Why do we write that negative 2 up there? Because we just learned it that way from Chem 2. We have a group number of 6. 2, 4, 6, 8. No bonding. 6 minus 8 is negative 2. All right, since I'm about out of time, I'm really heartbroken because this gets me real excited because Chapter 2, we talk about a little acid-base thing, and in OChem, we can make anything acid. We just pull hydrogens off. What is the conjugate base of hydroxide? Please don't tell me the hydronium ion. What is the conjugate base of the hydroxide ion? Oh, boy, nobody's shouting, raising their hand.
It's been a while.
No, okay, the conjugate base of hydroxide is oxide. Conjugate bases have 1 less proton. So the conjugate base of water is hydroxide. The conjugate base of hydronium is H2O. Conjugate acid of H2O is H3O plus charge. So in OChem, I can call this an acid, pull off a proton, leaves that as a conjugate base. All right. Any questions? So no lab today or tomorrow?